We know that if we put two objects with different temperatures in contact with each other, heat is going to transfer until they reach the same temperature or thermal equilibrium. In this lesson, I want to try to look at some of the rules regarding that. So we're studying heat. Heat we know is a form of energy. The symbol for it is Q, and the unit on it is the joule. What's the rate of heat transfer? Well, the rate of anything is that quantity per second. The rate of position is velocity, meters per second. So the rate of energy will be joules per second. The symbol would be delta Q over delta T. Again, the unit is joules per second. And you've seen joules per second before. That is also the unit of power. And usually we write that as watt instead of joules per second. And this very much is a power. It's how fast energy is being transferred. So I'm going to pause the video. This is going to be our dependent variable. And we're going to try to think of what other variables might affect how quickly this happens. We're then going to try to develop a model that puts all the variables we come up with together, and we're going to test it using data. So go ahead and pause the video. I'll do the same. And you list all the variables about this window and these rooms and the surroundings that you think might affect the rate of heat transfer. All right, so here's what I came up with. I said that the temperature difference is probably going to matter. If it's really hot inside and really cold outside, heat's going to transfer a lot quicker than if they're both pretty close together. I said I think the area of the window is going to matter. A bigger window and a little window are going to have different rates. And I think the thickness matters too. I also think the material matters. And if we're developing a model, we have to account for that somewhere in our model, but it's not clear to me how to do that yet. So what I want to do is try to come up with a linear equation that relates these variables to each other. And to do that, we obviously need to pick what our independent variable is going to be, what one we're going to change. And the one that I think we can change pretty easily for a single room and window is we can change the temperature difference. So this will be our independent. So we'll take same window, we'll have different temperature differences between inside and outside, and we'll keep the rest of the stuff constant, and we'll see if that somehow, if we can make a linear equation for that. So how do we do that? Well, the equation for a line is y equals mx plus b. And my independent variable x is going to be delta t. And that's my independent variable. My dependent variable y is going to be delta q over delta t. So the slope is going to contain all this other stuff. So let's try to go with that and see what we get. How do we think area is going to affect heat transfer? Well, I really think if I have a bigger window, heat's going to transfer quicker. I get cold standing by big windows in the winter, and that suggests to me that heat is escaping through those windows. So I'm going to say that I expect area to be directly proportional to heat transfer as well. Thickness, I think, is the opposite. I think if I have a thicker window, that's going to slow down the transfer of heat. So I'm going to put the thickness of the window, L, on the bottom of this equation. How do I account for material? Well, this equation is probably not good enough yet. If we look at the units here, this is meters squared times Kelvin over meters. So we have meters Kelvin, basically. it's not clear that that's equal to joules per second. So there's probably some constant here. And that constant is going to be the thing that really tells us about material. So I think different materials, glass, plastic, they're going to have a different constant here. And that's how we're going to account for some materials transferring heat quicker. So if this model is correct, and there's no reason to assume it is yet, other than it sort of, we have a hunch it is. If I make a graph and I put rate on that axis, temperature difference on that axis, I should get something linear. So I guess in order to do this, we need some data. So here's some sample data I created. That's not my sample data. That is. And basically, I'm going to ask you to calculate a delta T from this. And then I'd like you on paper, on graph paper, to make a plot, again, with this on the y-axis and then delta T on the x-axis. So go ahead and plot that data and draw a best fit line for it. And let's see if we can solve for what K is. All right, so here's my graph. And notice I did get a linear equation, which means I'm comfortable in the idea that delta T is directly proportional to the rate of heat transfer. Honestly, were I to really want to justify the other things in the equation, I would need to look at windows of different areas, windows of different thicknesses. I'd have to collect data on those as well. So this doesn't justify where they are in the equation, but it does show a linear dependence of temperature difference on rate of heat transfer. So according to the model I came up with, the slope of this line should be equal to area over thickness times K. Since I know the area and the thickness, I should be able to solve for K by getting the slope. So I did that. I picked 2 points on the line that are not data points. I found a slope. Since the slope is supposedly equal to K times area divided by thickness, that enabled me to solve for what K is. And I got 1 as my constant, and that's because this is sample data that I made up. I didn't actually collect this data. But in general, this would be different for every material. So hopefully this is now making you feel like we've justified a little bit our model. Again, heat transfer depends on material, depends on area, depends on thickness, and it depends on how different the 2 temperatures are.